In this project, we'll give the Raspberry Pi a basic sense of sight. With a camera and ready-made vision tools, it can recognize faces, objects, or colors, then trigger real-world alerts like LEDs, buzzers, messages, and eventually robot movement. You've already built the main pieces: ESP32 projects for sensing and connectivity, Arduino projects for dependable control, and Raspberry Pi projects for camera-based computing. Now we'll connect those ideas into a smarter robot. The camera will do more than capture an image. Eye vision will interpret what it sees, recognize something meaningful, and trigger a response like movement, signals, or alerts. Here, the camera becomes the robot's eyes. A live image comes in from the Raspberry Pi camera or a USB webcam, and the program asks a simple question. Do I recognize something useful? That might be a face, a specific object, or a color target. When the system detects the condition it is looking for, it responds automatically. An LED might change color, a buzzer might sound, a label might appear, or a servo might move. The mission is simple. See something important, then react. Computer vision works by treating video as a rapid sequence of still frames. The Raspberry Pi captures one frame, prepares it for the model, and searches for learned patterns such as faces, bags, colors, or bicycles. When something is detected, the result is usually a label, a box around the object, and a confidence score. The key step comes after detection. Our program uses those results as inputs for decisions such as sending an alert, dispensing something, or opening a gate. Before writing code, build a reliable foundation. The Raspberry Pi needs a camera input, either the camera module or a USB webcam, plus the output parts you plan to control, such as an LED with a resistor, a buzzer, or a servo. On the software side, make sure Raspberry Pi OS, Python, OpenCV, and the GPIO library are installed and working. Then choose your vision method: a face model, an object model, or a simple color threshold. Most testing problems come from missed setup steps, not bad logic. A camera frame is just raw material. Before a detector can understand it, we often clean it up, like wiping glasses before reading. Resizing makes each frame smaller, so the Raspberry Pi has less work and can respond faster. Color conversion puts the image into the format the model expects, such as RGB, BGR, or grayscale. Lighting matters too, because shadows and glare can hide important details. A steady, focused camera gives the algorithm consistent information. Better input usually means better detection, even before changing any code. For a beginner project, face detection is usually handled with a pre-built model rather than built from scratch. A model such as OpenCV Haar Cascades has already learned visual patterns that commonly indicate a face, including the arrangement of eyes, nose, and mouth. Your program sends each camera frame to the model, and the model returns locations where faces appear. Those locations can be drawn as bounding boxes. The important distinction is this: detection only says, there is a face here. It does not identify who the person is. The program begins by opening the camera and loading the trained face detection model. Then, it enters a continuous loop. Each cycle grabs a fresh frame, runs detection, and checks the result. If the list of detected faces is not empty, the code draws a box around each face, shows a detected label, and can trigger an output like a light, buzzer, or access signal. If the list is empty, the else path keeps outputs off and reports that no face was detected. This simple if-else decision is the core control logic. Object detection does not always require a complex AI model. In many classrooms, color detection is the most reliable first step because it is fast, visual, and works well with simple objects. Shape detection adds more challenge since lighting, shadows, and camera angle matter more. Pre-built models can recognize everyday items, but they usually need stronger hardware and more testing. The best choice is the one students can run consistently. Reliable results create better investigations than impressive tools that fail half the time. Color detection is practical because the Pi does not need to understand ball or duck. It only asks, which pixels look red? We choose a color range, usually in HSV, then create a mask where matching pixels become visible and everything else is ignored. From that mask, the program finds connected regions, picks the largest one, and draws a box around it. This works well for bright objects under steady lighting. If shadows or reflections change the color, adjust the range, or improve the light. A vision system usually reports three pieces of information when it detects something. The bounding box marks where the item appears. The label names what the system thinks it is. The confidence score shows how sure the model is, not whether it is definitely correct. A high score can still be wrong, so test with different examples and watch for misdetections or false detections. Once the Raspberry Pi understands what it sees, it can make the robot react. A detection result becomes a simple decision. If the target appears, turn on a green LED, beep the buzzer, or show a message like face found. If nothing is detected, show red. While searching, use blue. The same result can even drive a servo, so the robot turns toward an object instead of just reporting it. Detection alone is not enough. The robot needs decision rules that translate what the camera finds into one clear action. In code, this is usually simple if-else logic. If a face is detected, turn on the green LED. If a red object is detected, buzz twice. Else, if nothing has been detected for 5 seconds, display searching. The important part is consistency. Each condition should have a predictable response, and repeated detections should not create messy, overlapping outputs. Before you trust a computer vision project, test it the way the real world will test it. Try different lighting, distances, backgrounds, and camera angles, not just the easiest case. When something fails, debug systematically. Confirm the camera is connected, the required libraries are installed, and the detection settings match your task. Also, use cameras responsibly. Ask permission before recording or detecting people. Never build tools meant to embarrass, track, or judge classmates. Good vision projects are accurate, safe, and respectful. You've now connected the full vision pipeline. Capture an image, detect something meaningful, make a decision, and trigger a response. Whether you used face detection, object detection, or color tracking, the key idea is the same. Camera data can control real hardware. Next, we'll put that intelligence on wheels with an AI vision rover.